Welcome everybody, my name is Rukowska, this is Wojtczuk. We're gonna present attacking Intel Trusted Execution Technology today. And we are from Invisible Things Lab, which is a small consulting company. So today we're gonna talk about 4 subjects. First, about trusted execution technology and trusted computing, what it is, why we like to have it. Then we're going to talk about attacking trusted execution technology. We're going to show you some working exploits. And then we're going to talk about implementation bugs, which turn out to be crucial in exploiting those TXT in preparing this attack. And finally, we're going to talk more about TXT design problem, because our attack exploits both the implementation problem and design problem. So let's start with a short introduction to trusted computing and trusted execution technology in particular. So the basis of trusted computing is a TPM, Trusted Platform Module chip, which is a passive, I'm stressing the word passive I/O device, which used to be located on LPC bus. These days it's usually located in, it's part of the Nord bridge. It's part of the chipset. Anyway, it has special registers which are called PCR registers, which we're going to talk about in a minute. And it basically does, the most interesting things it can do is sealing, unsealing, and sometimes quoting. And we're going to discuss it just in a moment. So PCR registers. PCR registers are somewhat funny because one cannot directly write to a PCR register. One can only extend a PCR register. This is, the extend operation is, illustrated here with this equation. The whole idea about extending is that a single PCR can hold multiple results. We can send 1, 2, 3, 4 measurements to PCR, and PCR will still contain a hash. This hash will be unique to the sequence of values that have been stored in a particular PCR. And of course, it's computationally infeasible to set PCR to some specific value that we would like to have. So if we want to set PCR to OX11223344 whatever, we cannot really do that. What we can do, we can only store values in PCR and see what its value will be. And of course, if we extend PCR with something and then extend it with something else, this is not equal to extend it with something else and then with something. So this is used for sealing and unsealing operation. We have TPM chip, and we have some subset of PCRs. I chose PCR 17, 18, 19 just because they play important role in trusted execution technology, which we're going to talk about later. So let's assume that some values have been stored in those 3 registers. Then we can tell TPM to seal something in itself, for example, crypto key. And then TPM will allow this value to be unsealed, to be extracted, only when those PCR registers will match the values that have been when the sealing operation took place. And we're going to show you some live demos that basically use TPM seal and unseal programs. So you see an example. Well, this is a piece of text. So we want to seal a piece of text to a TPM or by a TPM. So we just echo secret, TPM seal data, this is standard in, and we seal it to my secret blob file. And we say we want to seal it to value of PCR 17, 18, and 19. And then, assuming that in our system PCR registers are exactly the same as they were during the seal operation, we can unseal it. If for some reason PCR registers are different, have different values, the unseal operation fails. And similarly, we have a quote operation on PCR that can be used to securely report the state of the PCR, which means the state of PCR registers. The quote command generates, well, not a packet, generates a blob that is digitally signed with TPM internal key and contains the values of PCR registers. And we can use only a subset of those. So what is it used for? First use of TPM is static root of trust. Static root of trust measurement can be used to implement secure boot this way. We have a TPM chip, we have those PCR registers, and we have a boot sequence. Boot sequence starts with a BIOS code booting. If you want to do this really securely, we want to have some piece of immutable code, some piece of BIOS code that is stored in ROM, read-only memory, that cannot be reflashed for security reasons. This little piece of BIOS code is sometimes called CRTM, Core Root of Trust Measurement. So this piece of code, what it does first, it measures itself. And what is in PCR1? I forgot what is in PCR1. You'll see a table just in a moment on the right. What is more important is just in the next step, just before it hands the execution to BIOS flash, which contains all the BIOS that is reflashable, it first measures the BIOS. When I say measure, it means calculate the hash on code and read-only data. So we calculate hash of the code of this BIOS, and before we pass execution to this code, we store this measurement in PCR 0, for example. This is a convention. I can choose any PCR I want. Just by convention, you're going to see a little table on the right just in a moment that specifies which PCRs are used for what, usually. So these dotted lines are PCR extend operations. Continuing with this, BIOS flash usually or sometimes can also initialize some PCI EEPROMs. So again, before allowing them to execute, they need to measure them and then execute them. And the hashes are stored in different PCRs. And then we have bootloader, so BIOS, before passing execution to the bootloader, whatever it is in the MBR, again, it calculates the hash of this thing and stores it in, let's say, PCR4. And bootloader can measure OS kernel, etc. The whole point is that if any of those blocks, if any of those things have been compromised, hooked, infected by a virus, whatever, then the hash value, the measurement of those blocks would be different. That would result in some of the PCRs being extended with a different value, which means the resulting value of PCR would be different. Which means that if we sealed something before there, now the system, which is booted with infected configuration, compromised configuration, would not be able to unseal data from TPM. We're going to discuss those scenarios just in a moment. This is the convention. By convention, PCR 0 is used for CRTM and flash measurement. 1 is for chipset config. 2 is for optional ROMs. PCI config, PCI devices config. PCR 4 is for bootloader, etc. This is just a convention. So SRTM in practice. Disk encryption. Microsoft BitLocker works exactly this way. So disk is encrypted with symmetric algorithm using some key K. And this key K is sealed into TPM using the particular PCR registers that have been recorded when the system was clean, when we know the system is clean. And then every time we boot our system, only if the PCR registers, which means the BIOS, the bootloader, everything, was exactly as it was before, the hash of it was exactly as it was before, only then the PCR registers will match, and only then the BitLocker will be able to extract, to unseal the crypto key from the TPM. The problem with this scenario is that the key, the decryption key, must be present in memory all the time, because if we consider on-the-fly disk encryption, well, the OS kernel does the decryption on the fly, which means the kernel has access to the crypto key all the time. Please note that the TPM itself does not perform decryption. This is not crypto accelerator. This is just key storage. So a malware can sniff it. So to get around this, we have another scenario. Another scenario, which is not implemented in any widely used product these days, but could be, is this. Users, during installation, we take a picture of ourselves using the built-in camera. This picture is stored in user directory and encrypted with a key that is sealed to a TPM. And again, it is sealed using the PCR registers that have been recorded during the installation when the system booted cleanly, when the system was clean and it booted. And then, every time we boot the system, only if BIOS, bootloader, OS kernel, everything was okay, if the hash is matched, only then the PCR registers will have correct values, only then the TPM will be able to unseal the key that was used to encrypt the picture, and only then let's say the OS would be able to show the picture. So if somebody infected our BIOS while we were taking a shower, we would, and then when we boot our system, we would not be able to see our picture. Another scenario is to use remote attestation instead of TPM sealing and unsealing. But this scenario requires to have a central corporate monitoring, well, let's say server. So every computer in corporation needs to authenticate to a central monitoring station with the quote command, which, as you remember, has the PCR values signed with TPM internal key. So only if the only if the correct system booted, only then the TPM will sign correct PCR values. And of course, if the system boots and the PCR are wrong, or the system is present in the network and has not authenticated, we can cut it off. So problems with static root of trust are those. First, completeness. We need to measure every possible piece of code that might have been executed in the system boot. If the attacker compromised anything in this chain from the core root of trust, then the attacker can fake the measurements of lighter, can fake the measurements of the lighter, can fake the results of the later measurement. And this raises the problem of scalability of the above. And because of the problems with static root of trust, so the problem with maintaining the chain of trust for a longer period of time, we have another approach which is called dynamic root of trust measurement. And this is just to address those very problems of SRTM. And DRTM works this way. We might have some system, and this system might already be booted. And there might be some programs running, and also some evil programs, some malware in the system, so we can have viruses, rootkits, whatever. And then in this system we place a little piece of code. This piece of code, I call it VMM, Virtual Machine Monitor, because usually we use this mechanism to start a virtual machine monitor, but this can also be OS kernel or OS loader. So whatever we have here, we want to become something privileged. the VM monitor or the OS kernel. But right now, there is no protection of this piece of code from the system. So the rootkits, the viruses, whatever that is in the system can compromise this piece, can modify this code at will. There is no protection at all. And then we have this magic new instruction. And since now we focus on Intel processors, and this senter is one of the new instructions that trusted execution technology introduced. So we have this magic new instruction senter, which does just that. It takes as an argument the address of this VMM that right now is unsecure, and loads it in this way that it places in some memory. This memory gets protection from everything, from the CPU, from the other CPUs, from all the I/O devices, so from DMA attacks. And this is, you see this black border around it. So this symbolizes the protection that has been applied to this VMM piece of code. Of course, just the moment before we executed senter, some of those viruses here might have compromised VMM. It might have happened. However, senter, before handling execution to this VMM, does one more thing. It extends PCR18 with the hash of this code. And before extending it, it actually resets. It resets PCR18. It also resets PCR17, but extends it with something else, which I don't want to go into details right now. So it places the hash of VMM into PCR18 and then secures the memory, and then handles execution to this VMM, no matter if VMM has been compromised or not. So senter does not check the value that is in PCR18. Whether it was or it wasn't compromised, VMM will get execution and will get protection. However, now, if we sealed some secret, some important secret, let's say disk encryption key, into TPM, to PCR18, to the specific value of PCR18, to the value that should be result of measurement of a correct VMM, only then VMM will be able to retrieve this secret if it hasn't been compromised. If it has been compromised just before loading, just before being loaded, it would not get access to the secret key. So, for example, would not be able to decrypt the disk, or would not be able to display the user's picture, or will not be able to report configuration using the quote command. Exactly the same as previously. If you think about it, this is amazing. This is effectively resetting the computer without actually resetting it. This is the core new functionality of Intel Trusted Execution Technology. Ability to securely load a piece of code from potentially compromised system. So it gives us a tool to securely create a VMM or kernel in a potentially unsecure system. So please read the slide again, and we're gonna switch now, and Rafa will tell you about T-boot, which is implementation from Intel that uses this new instruction.
Okay, so the bottom line, if you got lost in the middle of this explanation, which was lengthy, and it's necessarily lengthy, because this technology is complex. It's simply complex. It's difficult to, well, summarize it in 15 minutes. So these are the key points to remember. And if you're able to remember these lines, you should be able to follow up with the rest of the presentation. So the TXT-late launch can transfer from unknown, unmeasured, untrusted state to known, trusted, measured state without a reboot, which is a very useful functionality. The key point is that the system state, or the trustedness of the state of the system, can be verified reliably, as reliable as TPM can be, and possibly verified remotely, which is a very nice feature, because all important components for instance, hypervisor, kernel, etc., which are started using the late launch, the hashes of these components are loaded into the TPM PCR registers by senter instruction or by the following components. So these are the crucial facts. Okay, so this was the theory. So now let's have a look at the actual implementation, which is named tboot. It was written by Intel employees. The full source code has been released along with the documentation of way to go Intel guys in this case. So the execution scenario is, as you may expect, like that. The bootloader configuration, say group, should be modified so that instead of directly executing a VMM, for instance, the Xen hypervisor, let's just focus on Xen for clarity, we will execute tboot. And tboot is supposed to conduct all the necessary steps required for the late launch functionality of TXT. So it will, well, fill out the necessary data structures, etc., etc. And then it will execute a center instruction, this key component of TXT. Again, a center instruction will measure the tboot image and hand out execution to tboot measure launch environment. Then tboot additionally applies more measurements. It measures the Xen hypervisor itself. It also measures the Linux kernel used for domain 0 along with the initial RAM disk. So again, all the important components, all the privileged components are measured during the late launch. And again, these measurements are stored in PCRs. So you would like to see a usage example. First, the legal scenario. We will boot a trusted Xen. Let's image that this is the first time the system is used at all, so we may assume it has not been infected before. So we boot the trusted version of Xen, built by, well, administrator, and see what happens. Okay, so you can see that hypervisor was built by root. And now we can use the seal operation. It can be implemented by the TPM seal data utility, which is a part of the Trover suite. So again, as you saw before, we specify the secret on the standard input, and again pass appropriate parameters to the seal data operation, particularly specify the values of index of the PCRs registers. And when you have done it, we can use the TPM unseal data to, well, retrieve the secret. And of course, because the system state didn't change between these two invocations, we can successfully retrieve the message. We can try to run the hypercall backdoor. This is the implementation of the rootkit or backdoor, whatever you call it. We wrote for this test purpose. And of course, it complains it doesn't work. It says that the relevant hypercall relieved function not implemented, which is what you would expect from the clean system. And similarly, there is nothing suspicious in the Xen logs. Well, the system is clean. Now, what happens when we try to boot something else? Say the attacker managed to, well, build a Trojan version of Xen and somehow managed to change the boot configuration so that this Trojan version of the hypervisor is booted. So what happens? You can see in the log that someone else built this hypervisor. And this time, of course, this command succeeds. Apparently, all the components required for the functionality of this backdoor are present. And you can see in the logs that, say, this backdoor is capable of writing anything to the Xen logs. It also means it can perform arbitrary operation on behalf of the Xen hypervisor, which means that the attacker and the backdoor has full control of the system. But luckily, the TPM unseal data will fail. It will fail. More precisely, the TPM itself will refuse to release the secret because the values of the PCR register has changed. And again, I will probably repeat it a couple of times more during the course of the presentation. That's, well, the salt of the TXT, the essence. That's how it is supposed to work. Yeah, I already mentioned that again, only if we booted legal system, expected system. The secrets can be unsealed, remote attestation will work properly, etc., etc. Okay, now some live demo, say, not live, but keystroke capture. Essentially exactly the same, just to give you opportunity to...
It's live because it's moving.
You know, it looks more real, right?
Just know that what we sealed here in TPM, we sealed some stupid text, but it could have been disk decryption key that is used to decrypt the partitions, right? So the inability to unseal them would basically be obvious for a user. The system would not work.
This is a very important message. If you can see this message, the system has booted without change. The intact system has booted, right? So that's what it is all about. If you are able to unseal the secret with the help of TPM, it means the system configuration has not been altered.
Or this could be user's picture encrypted, right? The key to decrypt the user's picture. So every time administrator boots the server with Zen, for example, he or she will not see the correct picture and will be alarmed that something is wrong.
And again, it's possible to unseal the data. The backdoor will not work. Okay, let's save some time. And again, there will be nothing in the logs. Okay, the example number 2 is booting an untrusted version, modified version of the hypervisor. And this time, of course, it's well, just for clarity, we changed the name of the user who compiled the Xen. We could leave it the same, just to make it obvious that something has changed. And the hypercall backdoor will work. There will be a message in the logs that we control this running hypervisor.
This is just a patched version of Zen, infected by attacker.
So we assume that an attacker was able to boot another version of Xen, possibly Trojan, right? But still, the unseal operation will fail. And because it will fail, we are able to spot the intruder. One important fact is that even if the chipset and the CPU support TXT extensions and the system comes equipped with the TPM, none of these components are forced down your throat. It's not obligatory. The system can be booted normally without executing the center instruction. But again, the whole purpose of using the center instruction is get the proper measurements into the PCRs. So legal user will want to execute the center instruction to get the proper measurements in PCR and be able to authenticate via remote attestation or by unsealing the secret. Yeah, it's very similar to SRTM, but the only difference is that this time the chain of trust is significantly shorter, right? It's more manageable. Again, it's worth stressing that, well, so some people have some prejudices about TPM, that TPM is able to control your machine, such things like that. And we would like to stress that you don't have to use TPM, you don't have to use the center instruction, you don't have to use the TXT extension. You can use hardware in whatever way you want it. But if you change the configuration and the suitable steps have been taken before, like sealing a secret or generating an attestation key, you won't be able to lie about it. You won't be able to lie to some external entity that you haven't changed the configuration. And that's very, very useful. Okay, TXT is obviously Intel-only technology. AMD has something similar named Presidio, and it's really, really very similar. For instance, it also features a new CPU instruction named SKInit. We haven't looked at Presidio at all. We assume it's very similar. If there is some demand or requirements, we can try to see how it's like. Okay, another point really worth stressing. TXT is not, the silver bullet that will eliminate all the malware. No, really, by definition, it is not. It provides one thing, and it provides it well. It provides launch time protection. If you use TXT, you won't be able to change the boot sequence. But TXT does nothing against runtime attacks, against runtime compromise. So here you have an example. The system has been booted securely using SRTM or DRTM. So immediately after the system has booted, it was clean, it was fine. But then it's possible that there is some weakness in the hypervisor, say buffer overflow or any other coding error, which enables some evil entity to, exploit it and take control over the hypervisor. TXT does nothing to prevent that. Simply, it's not in the scope. So you have to be aware of that TXT provides one thing, the integrity of the boot process, but nothing about runtime protection. Finally, of course, there are technologies like VTD or VTX which are supposed to make the runtime protection of the hypervisor, etc., feasible. But again, these are not magic final solutions. Of course, particularly VTD is a very important component if you want to have a secure system. But again, automatically, if you just switch these options in the BIOS to enable VTD and VTX, your system doesn't get immune to all attacks. Particularly in the last edition of Black Hat USA, in our 3 talks, we showed at least 2 different attacks on the runtime attacks on the running hypervisor. So again, you must be aware of the limitation. Again, to sum up, TXT, even considering all these limitations or things which are out of the scope, we think it's exciting new technology. It really is not by itself a complete solution, but it's like the foundation upon which you can build more advanced solutions. And it's required foundation, because if you cannot trust the system state immediately after the boot, then you cannot reason anything about the system. So this is really important building block when you try to build a secure system.
Yeah, so let's stress it. TXT is really cool. It's one of the most breakthrough technologies in security on PC platforms that we see. We think it is. So let's now talk about attacking TXT. First, the question: what is more privileged than kernel code? Ring 0. What it is? Well, obviously it is the hypervisor, VTX hypervisor. Usually we call hypervisor ring -1, although ring -1 is not really a correct expression. It basically shows that hypervisor is something above the kernel. So now, what is more privileged than a hypervisor? Who knows?
System management.
Yes, system management mode. SMM, we call it ring -2. We just call it just
because it sounds nice, right?
Yeah, it sounds nice, and it shows that SMM can be even more privileged than a hypervisor, and it can be because SMM can access the whole system memory, including the hypervisor memory. SMM interrupts SMI can preempt the hypervisor, at least on VTX. That means that even if the processor is in the root mode, executing the hypervisor code, when the SMI comes, the hypervisor will get preempted and SMM code will get executed. And finally, SMM has unlimited access to I/O devices, which is not as bad as the first one, but still. Is this SMM a new thing? Of course it's not. It's been there since 386. So now SMM versus TXT. SMM gets loaded before the late launch, the S-enter execution, because SMM gets loaded at the very beginning of the system life, during the boot process, when the BIOS starts, because SMM is part of the BIOS. Actually, BIOS pretty much is SMM. It's some other code as well, but SMM is one of the main parts of the BIOS. So, does TXT measure currently used SMM? No, it doesn't, And it's good it doesn't, because it wouldn't make any sense even if it did, because running code is not that obvious to measure. We can measure code before loading it, because we can measure the text, the read-only data, the initialized data, but running code is extremely difficult to measure. I spent some years researching this topic, and it's simply infeasible. Does txt reload SMM on senter execution? So whenever we do the late launch. Did we say that senter execution is called the late launch? I'm saying it now. So senter is called late launch. No, senter does not reload SMM. That would actually make sense, but it doesn't. So how does senter deal with potentially malicious SMM? Well, it does not. So we have this.
And there's a moment when the audience should go like, woo.
Any Intel people here? Okay, so here we have again this Zen booting. I'm not sure if Rafał told you that tboot is actually part of Zen. It actually looks like an important part of Zen, because if you look at the main README in the sources, like 20% of the README file is devoted to tboot actually. So anyway, tboot is part of Zen, so we have this Zen booting using tboot here, and our attack we can work this way. We infect the OS loader. In this, we'll show you just in a minute how to do this. So let's assume that the OS loader, let's say grub, has been infected in this way that it will infect SMM memory, or inject some piece of malicious code into SMM memory, inject some shellcode into SMM memory, and now this code will survive the senter phase, and just after Zen gets executed, after the secure late launch, the code from SMM will modify it and inject some backdoor to Zen. And again, for backdoors in Zen, you can refer to our presentation from Black Hat Vegas last year. So this is the sketch of our attack. This is the actual shellcode. I'm not sure if you were not supposed to say that. I think you want to say. You want to tell me? Yeah, because Rafał wrote the shellcode.
Okay. So Joanna mentioned that we'll try to infect the SMM memory with some shellcode which will perform required action for us. And this is the actual code which in our implementation has been used.
Just want to show them one thing, okay? What we are showing you now is this thing here.
Right.
Sorry.
Okay, and in fact this piece of code is a little bit embarrassing. In fact, because when we wrote it, we didn't have a clear picture about how the SMM handler operates, what is the organization of the code flow. So we had to, well, do some things just to stay on the safe side, like saving the DS register, restoring the function epilogue. But anyway, the bottom line is that all that this piece of code has to do is exactly one thing, is to overwrite a single unused entry in the hypercall table. This is
of Zen.
Of Zen, of course. Hypercall table is a part of Zen. So this is the address of this hypercall table, and we override this entry with a certain address which unprivileged guest can control. So it can be like anything on 32 bits below 4 gigs and on 64 bits architecture. Even sufficiently, it can be sufficiently larger. Anyway, any address which can be mapped by the guest. So we think that today, when we know how this SMM handler actually operates, it should be as simple as that. Just two instructions that, again, do the same thing. Overwrite an unused entry in some function pointer table with a controlled value. But in fact, we haven't rewrote this exploit code because the current one works very nicely, so we didn't bother. Okay, what is the result of our attack? It will look like that. again, the legal system has booted, but this time the hypercode backdoor will operate correctly. And will operate correctly exactly because the SMM handler has overwritten the entry for hypercode 38. Okay, so you can see it's working. You can see something in the logs that we control Xen, but that's not too scary, right? We saw it before. You can achieve the same by simply changing the Xen version that has been booted. You can achieve the same by booting Trojan Xen. What is a little bit scary is that TXT says that nothing has changed. The boot configuration has not changed. And this is exactly what TXT should detect and prevent. You shouldn't be able to unseal the secret. So that clearly bypasses the protection which should be implemented by TXT.
So even if we loaded the system gets compromised immediately after it gets loaded. However, the sealed data from TPM are available. So we can display the user's picture, decrypt the disk, whatever. Use quote command.
Okay. There is one tiny thing which I glanced over in this demonstration. How are we going to infect the SMM handler? You may have heard that SMM handler lives in memory, which is protected by the chipset. Normally, CPU is not able to access this memory. And it happens we managed to find a way, so stay tuned. We'll discuss the details of this exploitation later. But for now, let's take some more moving letters, which is nice. Everybody likes that. Okay, so here an attacker modifies the group bootloader. It changes the file responsible for stage 2. And you'll see that some custom code is inserted to the code of bootloader. Particularly this Q35 fun function will be explained later. Okay, so we built the new group bootloader. Then we will have to install it to the correct place. Again, the whole point is that TXT measurements does not include group in this time. Because normally we shouldn't care, right? The whole point that we don't need to care for the whole boot chain. But in this time, and that's why we can change group bootloader without being noticed. Okay, and after the changing the bootloader, we reboot. And if you could have a look at the serial console, we should see the messages from the bootloader. This little command is supposed just to pass all the output from serial port to the standard output. And what will you see? So first, normal messages from group. We have only a single entry. Original Xen is booted, but then this inserted code starts executing. We have to enter PAE mode. Then we set appropriate chipset registers. We'll describe it later, which enable us to infect SMM memory, and then we continue booting, like nothing has happened. And then afterwards, what is the state of the system? And as explained before, all the privilege components that has been measured have not been altered during the time of the late launch. This crucial issue is that this SMM shellcode executes just after the late launch has completed. Okay, and again, hypercall backdoor works. You can see in the logs that there is some code which has total control over the hypervisor. And again, it's possible to retrieve the sealed secrets. And again, this is a crucial moment. TXT should detect that the altered version of the hypervisor is running, but it failed to. Okay.
And that's the attack. So, how to get into SMM? Quick history of SMM security-related research. So, 2006, Loïc Duflo at ConseQuest presented how to use SMM to bypass OpenBSD secure level mechanism. And also last year at Black Hat, Sherry Sparks and Sean Belton showed how to create SMM rootkits. What they have not showed is how to actually bypass SMM protection. Back in 2006, for Luik, it was just enough to simply ask the chipset to write to SMM, because most of the BIOSes did not properly lock, or did not lock at all access to SMM memory. Today, BIOSes set special locks, so they lock down access to SMRAM, SMM memory. So theoretically today, it's not possible to overwrite SMM memory. Even kernel mode code, even hypervisor code cannot not only write but even read the SMM memory. So if you attended Sherry Sparks' talk last year at Black Hat, they presented those SMM rootkits. However, at the end of the talk, they said they believe those rootkits can be applied only to systems from before 2006, because newer systems have SMM locked and they cannot really bypass it. And for newer systems, they said virtualization rootkits are a better idea. However, at the same conference, we also presented, we actually not presented, we just said we have discovered a bug in Q35, Intel Q35, which was one of the most recent chipsets back at the time, that allowed us to, for example, overwrite SMM memory. We did not provide details because back then the bug was not patched. A few weeks after the conference, Intel has patched the bug, and we have posted the uncensored presentation slides with details of the attack. And just today we are presenting another method to go. We are not presenting, but we are saying we have new one, and this one is still being patched by Intel and will be available soon. And at Black Hat USA we will present this, the details of this attack. However, if we think about finding bugs in SMM, because we want to get to SMM, so we want to exploit something in SMM, we have some little problem, because, well, we start from this point. We have no bugs in SMM, right? Because we're just starting. All the bugs have been patched. So we cannot read SMM. We not only cannot write, we cannot read SMM memory. We cannot read SMM memory, so we cannot actually look at the code, we cannot find bugs there. So we have a pretty decent vicious circle, which partly explains why no previous research has been presented about finding bugs in SMM code. So how did we get around this vicious circle? Did we use the soldering? So this is DQ35JOE Intel motherboard, which was released quarter 4 2007, which was one of the newest. Now we have Q45, which is a next version of this. So here, between the memory slots and the north bridge and the south bridge, you see the SPA flash, which we desoldered. This is a picture from our lab, one of our labs. You see that this is where the SPA flash was supposed to be. This is the SPA flash, and this is the programmer. And we put it into the programmer, and we scanned, we read the whole SPA flash memory. However, this looks promising, but the BIOS image is heavily packed. Actually, we managed to unpack it, but interestingly, we did this whole thing after we used another method, much simpler. So remember our Q35 bug from Vegas? The bug was this. So for the first time we're presenting those slides here at Black Hat. So this is two views of system memory. Processor view, CPU view, and the actual DRAM that is actually on the motherboard. So usually with systems these days that have lots of graphics memory, we have a little problem with shadowing MMIO memory, for example, from the graphics card to the DRAM. So if we have 1 gigabyte of graphics memory, or half of gigabyte, basically this DRAM that normally would be at the same addresses where the graphics memory is MMIO'd, this is all physical address space. Not virtual address space, just physical address space, that usually would be unused. So, because of that, for example, on Intel chipsets, on recent Intel chipsets, we have memory remapping or memory reclaiming, as it's sometimes called, which works this way. We have special this is remap limit, remap base. These are special registers on the NOR bridge in the chipset that we can set, and we can remap this unused memory to those addresses. So processor accesses physical addresses above 4G, for example, and those accesses are directed to the actual physical DRAMs that normally are inaccessible because of the MMIO. And now applying this to SMM, for Black Hat last year, we used the exactly same bug, but we just didn't present those details. But we put Zen hypercall here, Zen hypercall table address, and we were able to override hypervisor hypercall. Today we put the base address of tsec. Tsec, this is SMRAM, where SMRAM starts. This way, using mmap and just simple mapping this to some user buffer, we can read and write to SMM memory. So we used this bug. This has been patched. So this is the output of our exploit that Rafa will explain you. Just keep in mind, we use this all to be able to read SMM memory and find another bugs, because this has been patched by Intel a few weeks after Black Hat Vegas.
Well, just very briefly, the whole point is to configure the chipset registers so that the target of this remapping is SMM memory. And it happens if you configure remapping this way, the chipset fails to protect SMM memory properly. So first you retrieve the address where SMM memory lives by querying the chipset registers. Then you configure the remap limited, remap base registers so that SMM memory is in the remapped area. And you may remember that this patched group loader was setting appropriate registers, remap base and remap limit, exactly for this purpose, to set up the remapping which will target SMM memory. And when we are done with that, we can open devmem device, which helps us with accessing the physical memory. And you can see that at the beginning of the buffer, you have this nice 4D, 5A. Anyone remembers what it is in ASCII? It's MZ. And MZ, of course, is the beginning of the P file header, which means there is really some executable file within this memory region. And if you disassemble the generated dump, you can see that we dumped it to the tsec dump ben file. If you disassemble that, you can see that it contains RSM instruction. Well, the only piece of code on the whole earth which can have the business to call RSM is SMM handler, because RSM cannot be used outside of...
RSM stands for return from SMM.
Right. So it really is possible to, well, not only read the memory of SMM as seen here, but also access it in read-write mode. Okay, moving pictures, we'll skip it, right, to save time?
You want moving pictures? Do you want the moving pictures? No? Let's skip it.
Okay. Okay, so that's the way how we been able to access this SMM memory for the first time, right? It was at the beginning of the second half of 2008. And of course, Intel has patched this bug pretty quickly, especially assessing the size of the corporation, in August 2008. Well, so now what? I guess you're not overly excited about hearing about the bugs which have been patched half a year ago, right? So the more interesting thing is VU 127284, however cryptic it sounds. We had a quite a bunch of conversations with Intel at the beginning of December, and the first one of the first ones was, well, we believe that TXT is essentially useless, or it fails to deliver its promises if we consider the attacks originating from evil SMM.
Just want to read the disclaimer here. The dialogues between ITL and Intel have been presented here have been modified for brevity and for better dramatic effect.
But we didn't have to modify much, in fact. Okay, so Intel responded that that's exaggeration, of course, because infecting SMM is hard, right? There is this one bug half a year ago. It was patched, so only one bug during like 2
just
years.
again, disclaimer. They actually said it's difficult by today's standards. We just check it.
Careful wording is important in this industry. Okay, this statement seems justified. Just one bug during all these years. So what could we do? All we could do is change the landscape a little bit. So we let know Intel that we found a bunch of new bugs. It's like 40 plus in the current BIOSes. And we wrote two working exploits to demonstrate, well, exploitability of these issues. In fact, we have provided Intel with the details of these issues, again, at the beginning of December. Intel has confirmed that these problems affect a plethora of products. Unfortunately, they didn't specify exact models which are affected, but we suspect that all recent Intel mainboards can be affected, mostly because the bug is pretty generic. It's not something very specific to the implementation. It's simply, again, the result of certain design decision which is wrong. Again, because of this genericity of the attack, Intel believed that other BIOS vendors can be affected as well. And that's the reason Intel has contacted CERT Coordination Center, informing them about the problem. And this magic identification string is exactly the tracking number of this issue assigned by CERT. Of course, we won't be able to discuss the bugs in its full details because they are not patched at the moment. So the plan for today is to discuss them at the next edition of Black Hat USA. So stay tuned. More information will be coming as the bugs get patched. And just in case, maybe don't trust your SMM meanwhile.
So let's talk more about the TXT design problem. So just to summarize, we have design problem, which is to allow SMM to survive a center process. This is the design problem. And we have the implementation bugs in SMM that we use to infect the SMM. Those two things need to be in place for the whole attack to succeed. So let's talk about now this TXT design problem. Again, this dramatized dialogue between Invisible Things Lab, this is we, and Intel. So Intel says solution to TXT attack is called STM, which is going to be on the next slide. And we say, can we take a look at an STM? And they say STM is Okay. We're going to explain just in a moment why STM is actually hard to have. So, but yeah, it was supposed to be fun. Yeah, they said there was no market demand yet. Okay, STM stands for SMM Transfer Monitor. So this is the hypervisor, for example, Zen or Hyper-V or whatever. And we have virtual machines here. And then we have a special, another hypervisor that runs in parallel to this hypervisor, which is called STM. And the purpose of this hypervisor is to virtualize only one guest, the SMM, the platform SMM. So we want to sandbox SMM. We want to use the hypervisor, the VTX and VTD, to sandbox the platform SMM. So it cannot do much harm. For example, it cannot infect Zen hypervisor, like we did in our demo, right? So, however, issues. For us, STM seems to be non-trivial to write, because we need to take care about CPU, memory, and I/O virtualization. It's not trivial to write a hypervisor that does all those things. For example, our Blue Pill does only CPU virtualization, and already contains a few thousand lines, the most basic version. And here we also need to do memory. Yeah, it's simple it's not really that difficult as with Hyper-V, for example, or normal hypervisor, but still it is difficult. And also I/O virtualization. Also VMM to STM. Remember, there is VMM, for example, Zen, and there is STM. They work together. They need to communicate somehow. They need to agree on a policy. So this asks for a standard for the VMM to STM protocol. And of course, the biggest issue is no STM in existence as of yet. Also, we ask who should write an STM, because it was actually not obvious to us after reading. One more digression. When you read Intel specifications, there is a mention of STM, but STM is never defined what it really is. It appears in some TXT developer's guide, but it's not defined what it is. The only one place where it is defined is David Graurock's, who is Intel employee, David Graurock's book about trusted computing, which is a book about TXT from 2006. So anyway, who should write it? So apparently OM BIOS vendors should do this. Actually, Intel is a BIOS vendor. You can buy lots of Intel motherboards, and Intel motherboards do have Intel BIOS. Also, why should we trust BIOS vendors to write a bug-free STM if we don't trust they will write a bug-free SMM? Because the purpose of STM is to protect against potentially malicious SMM. Why we need to protect against potentially malicious SMM? Because we believe there might be bugs in SMM. Bugs because a vendor was not careful enough. So why should the vendor create a correct STM then, if it is supposed to be the same vendor? So the answer, the statement is that SMM must be tuned to each new motherboard. And this, of course, gives possibility to introduce some new bugs with every new release of every new motherboard. But STM could be written in a generic way. And yeah, that's a fair point. So the idea is to somehow split the BIOS into SMM and STM, STM being this generic protection, somewhat thin, very mature, well-audited part of code that will protect against SMM, that will be changing all the time, that will be not that secure. So Intel told us they do have STM specification that, for example, covers the VMM to STM protocol and also exactly specifies how to write it, but it's available only under NDA, and the reason for that was that it's still somehow in the under development. And they offered us a chance to read the STM specification, but they required signing an NDA, and we refused because we rather not tie our hands with NDA, because we rather wait for an STM to appear on the market and just try to break it, right? Intel might be right, claiming that STM is the remedy for our attack. We are not really saying that STM is some bullshit. I mean, this might be a proper way to solve the problem, although there seem to be lots of issues that we hope the specification actually addresses. There are some other issues that we are not sure, but again, we can't really say much about STM because right now it doesn't exist, and we just wait for a working STM. If you're interested in sponsoring further research into STM, just don't hesitate to contact us. Still, allowing TXT to work without an STM, which is the case, so making STM an optional component, was, in our opinion, a design error of TXT. It should be obligatory. Or the problem of malicious SMM should have been solved in a different way. So, similar, TXT, no doubt, is exciting new technology. It can really change the landscape. It's comparing to all the other innovations in IT security. This is really something. Intel forgot, in quotation marks, about one small detail, about SMM. Because actually, if you read some messages, for example, from Intel employees when they were introducing T-boot, they explicitly said that the whole point about T-boot and TXT was that you don't have to, for example, trust your BIOS. You don't have to trust your BIOS, your EEPROMs, your everything. You can just have a system that is untrusted, magic click, and it is suddenly one component is trusted. But they forgot about a small detail. And we found a demonstrated breaking into SMM that allowed us to bypass TXT. As a special bonus, our attacks against SMM can also be used for other things, like the rootkits, the SMM rootkits that have been presented last year at Black Hat, now becoming a reality on even a modern latest hardware. Intel currently is patching the SMM bugs, and we also hope this presentation will stimulate Intel and other vendors to actually come up with a working STM, which would be a solution to our attacks against TXT. Questions?
What are the performance issues of virtualizing SMM?
What are the performance issues of virtualizing SMM? I have no idea.
Because there is no STM yet.
Yes.
More of a comment. While we don't really have a lot about STM, there's another thing they keep referencing called dual monitor mode, which is the same thing. And you could get enough information from that to actually build an STM.
You need to repeat this. Do you want a mic? I was supposed not to...
Yeah, they don't really have a lot about STM in their documentation.
You're saying Intel does not really have a lot... Okay, but these are just speculations. I mean...
Well, in public documentation. But
yeah, in public there is nothing almost.
But in public documentation, they have another thing called dual monitor mode.
Yes.
It's the same thing, and you could actually get enough information from that to build an STM.
Okay, so that's a good point. In a public document, in a public specification, software developers guide, there is a whole chapter about dual monitor mode, which says how to create a second virtual monitor that will work in parallel with the first one. However, they do not specify protocol, what should be used to talk to each other, and there are no guidelines how to actually how to efficiently create memory, I/O, and CPU virtualization for the SMM. These are non-trivial issues. Of course, you can build it all by yourself, but that's not the point. The whole point about STM is to make it very simple, to be much simpler than SMM.
And
Yes.
also, I think they don't document what is the purpose of at all.
Yeah, that's right. This whole chapter, like 100 pages, and there's no single word. Why would anybody want to actually run a second parallel virtual machine monitor? Of course, now you know.
There's also the issue of what it might do to hardware vendors. That, like Microsoft, for example, has talked about how they're hesitant to go towards that direction, possibly breaking existing things because of it. There is no standard. Everyone's worried about how it might affect BIOS vendors and hardware vendors. They've also issued, Intel's also made rather vague pronouncements about perhaps even in some situations visibility even for hardware, like the JTAG debugger, is not necessarily what you expect in some cases.
Okay,
There's a lot that's gray.
you lost me. Okay,
What?
you lost me.
Okay, sorry.
If you could summarize it.
I was saying that there's the issue, the other issues, Microsoft has talked about system management, for example, a lot. And they know it's a vector.
Microsoft is talking about SMM a lot. Okay.
They know it's an attack vector, but they basically said they are not willing to, as the operating system vendor, do anything towards locking it out because they don't know what it might do to other vendors.
They are unwilling to add anything to the OS to lock the SMM. This is what you're saying?
They were unwilling to say that. All they were saying, they weren't suggesting. All they were saying is that they're aware of system management mode is an attack vector against.
Is or is not?
What's that?
Is or is not?
It's system management mode. I mean, you can hit the real hardware. Just what you were talking about. They're aware of these things. Their concern is they weren't saying they weren't doing it specifically. They basically said they were unwilling at the moment to consider doing anything that might impact other vendors, hardware vendors.
I'm sorry, but Microsoft is not the right vendor to talk about this because locking down the SMM is the chipset and BIOS thing.
Absolutely. But
Okay.
the operating system has a role in that. It does not.
I'm sorry?
Does the operating system have a role in that? I mean, it's with the loader. And so
I think you need to speak slower. You know, I'm actually from Poland, so you know. Okay. Okay. Yes.
Do you guys have EFI at all as far as does that solve any of the design problems with SMM EFI bootloaders?
EFI bootloaders. Okay. What about them?
You looked at whether that resolves any of the issues or provides more attestation for trusted boot.
Does the EFI-based firmware? No, we haven't looked at EFI at all. So, no. Okay.
Again, the whole point of TXT is to get rid of dependency of BIOS. So, particularly, get rid of dependency of anything that EFI might introduce, right? So that's.
We still have 5 minutes, right? Anybody can confirm this? Yes?
1.
5 minutes. Okay.
One question. Is that like a problem with also the static trust? If you have a thermodynamic trust, you have a static trust, that will not be possible, right?
Would it be? The question is, would it be possible with a static root of trust?
Yeah. So this is a problem with TXT, but not with trust computing technology. Oh, it's a problem with a DRTM, dynamic root of trust, and with like a static root of trust, because we will measure the graph, and then that will happen, correct?
Correct.
Well, but that was just that was like against DRTM. I mean, what would be the point?
Oh, okay. I mean, like, you know.
Okay, I got your question. Okay, yes, okay, that attack would not work against SRTM scheme. Yes, okay, yes, that's correct. Because SRTM would measure grab, and grab would find this infection, this piece of code that does SMM infection. Okay.
How many times has Intel tried to hire both?
The question was how many times Intel tried to hire both of us. I'm not at liberty to provide any answer to this. More questions?
We're trying to make an SMM as simple as possible. How do you make it complex? You have some sort of complexity measure of how.
Can we make SMM as simple as possible?
To the point it would be analyzable and much more complex.
But see, the whole point about TXT is to not care about BIOS, SMM, bootloader, everything. So it should. We always should assume that SMM might contain bugs. It cannot really be made so simple because SMM has to deal with lots of hardware-specific tasks that are often updated. New motherboard comes out, it has new temperature sensors, whatever. So it's really hard to have this code What was it?
It was the flexibility or modify. There'd be something that could just keep the not capital K would be their win. That would be
If they try to, but they cannot make SMM immutable. They need to update it with every new motherboard. This is what you're asking?
Well, I'm describing because of that issue. That's why the SPM proposal was.
They come up with the idea? Yes.
But even so, it's got this complexity threshold. But I guess my question is the same one only now applied to the SPM? And I think you already addressed it in your talk. Was how simple can it be in order for it to become analyzable?
How simple should STM or SMM be?
I'm asking a new question. Now, I guess it's how simple the SPM be, and I think that's your answer is going to be interesting. Can't say.
Your question is how simple I think STM can be? Yes? That's the question?
Well, I guess what
I'm saying I really don't know. For me right now, if I was to write STM just from scratch, just based on the documentation on dual monitor mode, I would say it's fairly complicated piece of software. 10,000, I would just say. C, 10,000 C. What do you think?
I have no idea, really. It's really complicated piece of code which really.
I came up with this 10,000 because I remember some very simple version of Bluepill without nested virtualization had about 3,000 lines of code. I think so. We need to add and that was only CPU virtualization. We need to add simple memory virtualization plus I/O sandboxing. So just a rough estimate. That's just rough, really, a guess. Okay, thank you very much.